As cosmic objects falls into a black hole, extreme forces heat them up to millions of degrees before they plunges to its doom and is lost forever. But while they are being devoured by the black hole, this matter generates X-rays that flicker at faster and faster speeds before stopping altogether. The reason behind this flickering pattern has been a mystery to astronomers for years, but new observations using NASA telescopes have helped explain the phenomenon, revealing it is caused by the material around the black hole wobbling as it is gobbled up. Researchers have found this wobble is caused by the movement of hot plasma found near the very center of the black hole. This plasma shines on material falling into the black hole, causing it to emit X-rays. But as the plasma is constantly changing its orientation, due to an effect proposed by Einstein's general theory of relativity, it affects the wavelength of the X-rays, which causes this flickering. When this flickering phenomenon was first observed, it was named the quasi-periodic oscillation. It was immediately recognized to be something fascinating because it is coming from something very close to a black hole, said Dr. Adam Ingram, from the University of Amsterdam, who works to understand QPOs. Researchers thought the phenomenon was caused by the material spinning as it falls into a black hole, undergoing an effect called the lens-stirring effect, proposed by Einstein's general relativity. This is a way rotating objects twist space-time, and drag those orbiting them. The tiny effect has been observed on objects around Earth. It is a bit like twisting a spoon in honey. Imagine that the honey's space and anything embedded in the honey will be dragged around by the twisting spoon, said Dr. Ingram. In reality, this means that anything orbiting a spinning object will have its motion affected. On Earth, the effect is so small it makes objects go through one complete precession cycle, the time it takes for the orbit to return to normal, once every 33 million years. Europe's Vega rocket measured the effect in 2012. But around a black hole, the effect is much stronger because of the intense gravity, meaning each cycle would take just a few seconds or less, the same period seen by flickering objects. We have spent a lot of time trying to find smoking gun evidence for this behavior, said Dr. Ingram. The researchers came up with a theory that suggests the hot plasma near the very center of a black hole, called the inner flow, which shines on the material and causes it to give off X-rays, was experiencing this lens-stirring effect. This hot inner flow shrinks in size over weeks and months as it is eaten by the black hole. Because the material surrounding a black hole rotates, the X-rays given off by material falling into it experience the Doppler effect. This is the stretching or squeezing of waves as they move away from or towards an object, and is the same reason ambulance sirens sound different when they are driving towards or away from you. When material is on the approaching side of the disk, its X-rays are squashed, or blue shifted, and when materials are on the receding disk, the X-rays are stretched, or red shifted. If the inner flow is precessing because of the lens-stirring effect, it would sometimes shine on the material moving away and sometimes on the material. The smaller the inner flow becomes, the closer to the black hole it would approach, and so the faster its lens-stirring precession cycle would be. This is a major breakthrough since the study combines information about the timing and energy of X-ray photons to settle the 30-year debate around the origin of QPOs. The photon collecting capability of XMM Newton was instrumental in this work, said Norbert Schuttel, ESA project scientist for XMM Newton. The researchers tested this theory by watching a black hole using ESA's X-ray Space Observatory, XMM Newton. Dr. Ingram and colleagues from Amsterdam, Cambridge, Southampton and Tokyo watched the black hole H1743-322, which was exhibiting a 4-second QPO at the time. They watched it for 260,000 seconds with XMM Newton, and also observed it for 70,000 seconds with NASA's NuSTAR X-ray Observatory. The high-energy capability of NuSTAR was very important, Dr. Ingram said. NuSTAR confirmed the wobbling of the iron line, and additionally saw a feature in the spectrum called a reflection hump that added evidence for precession. After a rigorous analysis process, they saw that the X-ray line was wobbling in line with the predictions of general relativity. We are directly measuring the motion of matter in a strong gravitational field near to a black hole, says Ingram. This is the first time the lens-stirring effect has been measured in a strong gravitational field, backing up another aspect proposed by Einstein's general relativity. The new technique will allow astronomers to carefully map matter in the inner regions of accretion disks around black holes. It may also be a powerful way to test general relativity further, because the theory remains largely untested and gravitational fields is strong. If astronomers can understand the physics of the matter that is flowing into the black hole, they can use it to test the predictions of general relativity as never before. If you can get to the bottom of the astrophysics, then you can really test the general relativity, Dr. Ingram said. A deviation from the predictions of general relativity would be welcomed by a lot of astronomers and physicists, because it would be a concrete signal that a deeper theory of gravity exists.